Some places on the Earth actively resist human presence. The cold destroys machines, the ground moves, the air thins. Rescue becomes impossible, and yet against all of that, humans still build massive infrastructure in these environments. So in this video, we're looking at megaprojects constructed in the most inhospitable places. Starting with number 15, Antarctica's deep research outpost, Concordia Station. Sitting on the Antarctic plateau at Dome C, Concordia Station, more than 3,200 meters above sea level, it's roughly 1,000 kilometers from the nearest coast. It is one of the most isolated permanent research stations on the planet, jointly operated by France and Italy. The environment here is not just cold, it's physiologically hostile. Wind temperatures routinely fall below negative 80 degrees Celsius, air pressure is equivalent to standing on a high Himalayan peak, and for months at a time, it's completely inaccessible. Its construction began in the late 90s and required a level of logistical planning that few projects ever face. Every component, fuel supply, and piece of life support equipment had to be transported thousands of kilometers across moving ice from coastal bases. Once on site, the crews had to work in thin air and extreme cold, which limited how long people could safely work outdoors. The station itself is composed of two cylindrical towers raised above the ice on stilts. Now that design's not aesthetic, it's functional. Snow accumulation here on the Antarctic plateau never truly stops, and any structure placed directly on the surface risks being buried. Elevating the station reduces the snow buildup and allows the wind to scour the surface beneath it, and the cylindrical shape minimizes any wind resistance and heat loss, which are critical concerns in this environment. Living conditions are tightly controlled here. During the 9-month winter isolation period, the crew, typically around a dozen people, cannot leave, cannot be resupplied, and cannot receive medical evacuation. Every aspect of survival depends on redundancy and reliability. Power is generated by diesel engines designed to function in extreme cold. Heat recovery systems capture waste heat to warm the living quarters, and water is produced by melting snow. Concordia is often compared to a space station for a future Mars habitat, and for good reason. The combination of confinement and environmental danger make it a valuable analog for long-duration space missions. In one of the most hostile places on Earth, Concordia Station functions year after year, and it quietly produces data that could not be gathered anywhere else. It is a megaproject, not because of its size, but because of what it proves, that humans can design and operate complex infrastructure in conditions where survival itself is never guaranteed. Number 14. The Trans-Alaska Pipeline System stretches for about 1,300 kilometers from Prudhoe Bay on the Arctic Ocean to the ice-free port of Valdez in southern Alaska. Completed in 1977, it was built to move crude oil across one of the most challenging landscapes ever tackled. Along its route, the pipeline crosses mountains, earthquake zones, braided rivers, and huge expanses of permafrost that can shift and thaw unpredictably. In northern Alaska, permafrost remains frozen year-round, but even small increases in temperature can cause it to soften and lose structural strength. Burying a warm oil pipeline directly in frozen ground would have melted the permafrost and caused the line to sink or rupture. To solve this, engineers elevated much of the pipeline on vertical supports. Construction took place in a region with no existing roads capable of supporting heavy equipment. Entire access roads, worker camps, and supply systems had to be built first, often under winter conditions to minimize any environmental impact. Crews had to work in temperatures that could drop below negative 50 degrees Celsius, where exposed skin freezes in seconds and machinery becomes brittle. Engines had to be kept running continuously to prevent them from freezing solid, and welding steel pipe in extreme cold required specialized techniques to avoid cracking. The route does pass through some sensitive ecosystems used by caribou, bears, and migratory birds. Elevated sections were spaced to allow wildlife to pass underneath, and river crossings were carefully engineered to avoid disrupting any fish habitat. Since entering service, the Trans-Alaska Pipeline has transported billions of barrels of oil, and it's fundamentally reshaped Alaska's economy. It enabled large-scale oil production in the Arctic, brought revenue to the state, and showed that the long-distance energy infrastructure could be built and maintained in this kind of extreme cold. At the same time, it's a reminder of the trade-offs involved in developing resources in these fragile environments. Decades after construction, it continues to operate in a land that actively resists humans. Every winter, every earthquake, and every freeze-thaw cycle tests its design. That it remains standing is an example of engineering shaped by necessity, where the environment dictated the rules, and failure was never an option. Number 13. The Qinghai-Tibet Railway is the highest altitude railway ever built, running approximately 2,000 kilometers from Qining in Qinghai Province to Lhasa in the Tibet Autonomous Region. More than half of the route lies above 4,000 meters, and its highest point, the Tungula Pass, reaches about 5,000 meters above sea level. At those elevations, oxygen levels are roughly 40% lower than at sea level, temperatures swing drastically, and large sections of ground are permanently frozen. Constructing a modern railway in these conditions pushed the limits of civil engineering and human endurance. Work began in stages, with the most difficult high-altitude sections constructed between 2001 and 2006, with one of the primary challenges being permafrost. Engineers had to develop multiple solutions depending on local conditions, including crushed rock embankments designed to reflect heat, elevated bridge-like sections that allow cold air circulation beneath the tracks, and thermosiphons that actively draw heat away from the ground. All these measures were intended to maintain its stability rather than provide any temporary fix. Construction crews worked in environments where altitude sickness was a constant risk. Oxygen stations were established along the route, and many workers operated on rotational schedules to limit their prolonged exposure. But even with those measures, productivity was lower than at lower elevations, forcing the project to rely on scale rather than speed. Tens of thousands of workers and a ton of equipment were required to maintain progress during the short season. Operating the railway also posed some challenges beyond construction. Passenger cars were equipped with oxygen enrichment systems to reduce altitude sickness during travel, and windows were designed to block ultraviolet radiation, which is stronger at these higher elevations. Engines and braking systems, too, had to be adapted for the thin air, where combustion and cooling behave differently than at sea level, and maintenance crews continued to monitor the track stability year-round as the freeze-thaw cycles and seismic activity remain. Since opening to full service in 2006, it has transformed transportation on the plateau. Travel times between Tibet and the rest of China were dramatically reduced, and at the same time, the railway remains a controversial project due to its social impact, which is widely discussed and documented. But from an engineering standpoint, the railway is a clear example of infrastructure being built where conditions resist permanence. In one of the highest and coldest inhabited regions on Earth, steel rails now operate continuously across terrain that was once considered inaccessible. Number 12. The Sakhalin-1 project is a large-scale oil and gas development located off the northeastern coast of Sakhalin Island in Russia's Far East. This region lies within a subarctic climate zone where winter sea ice, violent storms, and seismic activity combine to create one of the harshest offshore operating environments in the world. Production facilities were designed to operate in waters that freeze seasonally, with drifting ice flows capable of exerting immense pressure on offshore structures. Fixed platforms were engineered with reinforced bases and sloped sides to deflect ice rather than resist it, and materials were selected to remain ductile at very low temperatures. One of the most technically demanding components was the extended reach drilling. From onshore drilling sites, wells were drilled horizontally beneath the seabed to the offshore reservoir, reducing the need for additional platforms in the ice waters. Some of these wells rank among the longest extended reach wells ever drilled, requiring control and advanced monitoring to maintain accuracy over these kilometers. Seismic risk added a layer of complexity. Sakhalin Island sits near active tectonic zones, and offshore and onshore facilities were designed to withstand earthquakes. Regular inspections and monitoring systems were integrated to detect any early sign of stress or displacement. Transporting oil from Sakhalin-1 represented additional challenges. Export routes had to function reliably through the icy seas, requiring ice-class tankers and carefully coordinated shipping schedules. And onshore pipelines crossed terrain subject to landslides and freezing temperatures, demanding constant maintenance. This Sakhalin-1 project shows how these kinds of megaprojects in these harsh environments depend on layered solutions rather than a single breakthrough. Ice, cold, earthquakes, and remoteness were not eliminated as risks. They were accepted as permanent conditions and engineered around accordingly. The result is an energy system that operates in a region where nature imposes strict limits and where long-term success depends on anticipating failure rather than reacting to it after the fact. Number 11. Located on the Kola Peninsula in northwestern Russia, the Kola Super Deep Borehole, less than 200 kilometers from the Arctic Circle, remains the deepest artificial point ever reached on Earth, extending over 12,200 meters into the planet. Although modest in surface footprint, it qualifies as a megaproject because of the extreme environment and the long-term scientific ambition behind it. Drilling began in 1970 under the Soviet scientific program with the goal of reaching a depth of 15 kilometers to study the Earth's continental crust directly. This location was chosen because the Baltic Shield is composed of some of the oldest and most stable rock on the planet, and what seemed geologically ideal on paper proved brutally difficult in practice. Unlike oil or gas drilling, the Kola borehole was a pure research project. There was no commercial incentive to simplify or shorten the work. Progress was slow and deliberate, and every additional kilometer introduced new problems that had never been encountered before. As the depth increased, temperatures rose far beyond expectations, and at the deepest point, the rock temperature exceeded 180 degrees Celsius, way hotter than models had predicted. This caused the drilling equipment to warp, seals to fail, and lubricants to degrade rapidly. Pressure was another major obstacle. At those extreme depths, rock behaves less like a brittle solid and more like a plastic material. Borehole walls began to deform inward, trapping drill strings and forcing repeated redesigns. Drilling mud formulations had to be constantly adjusted to maintain the stability of it, and even then sections of the borehole collapsed and had to be abandoned. Multiple parallel shafts were drilled, each branching from shallower depths after earlier paths became unusable. The project produced valuable scientific data. Researchers discovered unexpectedly high levels of hydrogen gas, evidence of deep groundwater circulation, and microfossils embedded in these ancient rock layers, which did challenge the assumptions about the limits of life. These findings were documented and published even as drilling slowed and ambitions were scaled back. By the late 1980s, funding had declined and the technical limitations became insurmountable. The borehole never reached its intended depth, and operations ceased in the early 90s. The site was later sealed, and today only a small capped wellhead remains visible on the surface. In a frozen Arctic land where engineers attempted to push directly into the Earth itself and discovered that the deeper they went, the less predictable the planet became, that's what makes the Kola Super Deep Borehole a megaproject. Not with visual impact, but with the extreme conditions under which it was executed and the physical limits it exposed. Number 10. The Atacama Large Millimeter Submillimeter Array, known as ALMA, is located on the Changanator Plateau in northern Chile at an elevation of about 5,000 meters. It is one of the most advanced astronomical observatories ever built, designed to study the universe in millimeter and submillimeter wavelengths. This location was chosen because it is one of the driest places on Earth, but that same dryness and altitude make it an exceptionally harsh environment. At this elevation, oxygen levels are reduced, and even healthy people can experience altitude sickness. Winds are strong and unpredictable, and the plateau is subject to occasional snowstorms, despite being located in a desert. ALMA consists of 66 high-precision radio antennas spread across the plateau, working together as a single instrument. Each antenna weighs about 100 tons and has to be positioned with millimeter-level accuracy. Transporting and installing all these structures required specially designed vehicles capable of moving huge loads across unpaved terrain at high altitude. Much of the assembly work was performed at a base camp around 2,900 meters, where oxygen levels are less extreme. Even so, workers followed strict medical protocols, including oxygen supplementation and limited shifts. Some tasks at the main array site could only be performed for a very short period before crews were required to descend. The environment here also influenced the material selection and systems design. Electronics had to function reliably in cold, dry air where static discharge is a constant risk. Mechanical components were engineered to tolerate large temperature swings without losing any precision, and power systems had to be stable enough despite the remoteness of the site. Water scarcity up here was another constraint. The desert here receives almost no rainfall, and all water used for construction and operations had to be carefully sourced, transported, and managed. The seismic activity too posed an additional challenge. Northern Chile is one of the most seismically active regions in the world, and Alma's structures were designed to withstand any significant earthquake without losing alignment. Since becoming fully operational, it's delivered groundbreaking results, providing insights into star formation, planetary systems, and distant galaxies. Its success depends directly on its location, yet that location also represents a constant challenge. In a place where the air is thin, water is scarce, and the margin for error is minimal, it shows how advanced infrastructure can function reliably, when every environmental limitation is acknowledged and engineered around rather than ignored. Number 9. The Dasu Hydropower Project is under construction on the Indus River in northern Pakistan. This region is defined by steep Himalayan terrain and seismic instability. It's an area where large-scale structures are exceptionally difficult to build and maintain, making this one of the most challenging hydropower projects currently underway. The dam site sits in a narrow river gorge carved through hard, fractured rock. Surrounding slopes rise sharply, creating constant risks of landslides and rockfalls. There's no margin for error here when working in a confined valley, where evacuation options are limited and heavy machinery operates inches from a steep drop-off. The seismic risk here is a defining factor of this project. Northern Pakistan lies on a boundary of the Indian and Eurasian tectonic plates, and the region has a long history of destructive quakes. Dasu's design has to withstand strong ground motion while maintaining the integrity of the dam, spillways, and tunnels. There is no nearby industrial base capable of supplying material or skilled labor at this scale. Cement, steel, fuel, and equipment have to be transported over huge distances through mountain roads that are frequently disrupted by weather or terrain failure. And the Indus River itself presents a constant challenge. During peak flow periods, water volumes increase dramatically, placing stress on cofferdams and diversion tunnels. Managing river flow while excavating foundations and constructing spillways requires precise timing and redundancy. Any failure during flood season could damage months of work and endanger lives downstream. Human safety is a persistent concern here. The region's remoteness means emergency response times are long, and weather conditions can prevent helicopter access. Security risks, too, have also affected construction schedules, which required additional protective measures. These factors increase the cost and slow progress, but they're unavoidable in this environment. When completed, Dasu is expected to generate thousands of megawatts of electricity, contributing to Pakistan's energy supply, and the scale and output classify it as a megaproject. Few places combine the extreme terrain, the seismic risk, the climate volatility, and logistics so completely. Every tunnel, foundation, and concrete pour has to account for forces that cannot be controlled, only managed. It's a great example of a modern megaproject where nature dictates the limits, and engineers exist solely to operate within them. Number 8. The Ice Cube Neutrino Observatory. It's located in the Amundsen-Scott South Pole Station in Antarctica. It's one of the most hostile environments. Unlike traditional observatories that sit on the surface, this one's built deep within the Antarctic ice sheet itself. It is the largest neutrino detector ever constructed, designed to observe subatomic particles that pass through the Earth from distant cosmic sources. Constructing it required working in extreme cold, total isolation, and conditions where even minor mistakes could not easily be corrected. The South Pole here experiences an average annual temperature of negative 49 degrees Celsius, with lows in the winter dropping below negative 70. For roughly 6 months each year, the site is completely inaccessible, and this level of isolation imposed some strict limits on construction. Ice Cube was built between 2005 and 2010 using a method that had never been attempted at this scale. Instead of excavating rock or soil, engineers drilled narrow holes up to 2,400 meters deep into solid ice using hot water drill systems. These drills melted through the ice using water heated to near boiling temperatures, creating the shafts that had to be completed and instrumented before refreezing began. Each hole took roughly 30 to 40 hours to drill, after which strings of digital and optical sensors were lowered into the ice. The timing was critical. Once drilling stopped, the surrounding ice began to refreeze almost immediately. If a sensor string was not deployed correctly or became stuck, there was no way to retrieve or reposition it. Every deployment had to work on the first attempt. Extreme cold makes materials here brittle, it degrades lubricants, and causes electronic components to fail unexpectedly. Power generation, water heating systems, and drilling pumps all had to operate continuously for weeks at a time. The human factors were equally challenging. Workers operated at a high altitude as the South Pole sits at nearly 2,800 meters above sea level. The shifts were tightly regulated and medical monitoring was routine. During the summer construction, crews worked nearly non-stop, knowing that the unfinished work would have to wait an entire year. Once completed, IceCube became a permanent passive instrument embedded in the ice. Engineers accounted for all of that by designing sensor strings that could tolerate gradual movement without losing alignment or functionality. IceCube has since confirmed detections of high-energy neutrinos originating beyond the solar system, opening a new field of astronomy. The clarity and stability of the Antarctic ice provide conditions that cannot be replicated anywhere else on Earth. Built in a place where rescue is impossible for months at a time, this one represents infrastructure created at the absolute edge of human accessibility. Moving on to number 7. The Norilsk Industrial Complex is located in northern Siberia above the Arctic Circle. It's one of the coldest inhabited regions. Built around vast nickel, copper, and palladium deposit, it represents one of the largest extreme industrial developments ever attempted in a polar environment. Norilsk is not a single facility, it's an interconnected system of mines, smelters, power plants, housing, and transport infrastructure operating year-round in these Arctic conditions. Construction began in the 1930s when the region was almost entirely undeveloped. Winter temperatures routinely fall below -40°C, and permafrost underlies nearly all the ground surface. There's no road or rail connections to the rest of Russia, and most supplies historically arrived by river during a short summer window or by air under difficult weather conditions. Structures couldn't rely on traditional foundations here. The heat from buildings would thaw the frozen ground and cause uneven settling. So engineers had to adopt pile foundations that were driven into stable frozen layers, elevating the buildings to allow the air circulation and reduce heat transfer into the soil. Mining operations here added another layer of challenge. Underground shafts and tunnels had to contend with freezing equipment, brittle materials, and ventilation problems, intensified by the extreme cold. Engines often had to be kept running continuously to prevent them from freezing, so power generation was essential for survival here, as well as production. The whole complex relies heavily on local power plants as external grid connections are limited. Any prolonged outage during winter would pose serious risks to both industry and people. The human environment was also equally demanding. Housing, hospitals, and public facilities had to function reliably in conditions where exposure can be fatal in minutes. Everything from building material to water and sewage systems had to be adapted for the extreme cold. Workforce rotation, specialized clothing, and controlled indoor environments became standard. Over time, Norilsk grew into one of the world's largest producers of nickel and palladium, and it made it economically significant despite its isolation. Unlike temporary research stations or seasonal operations, Norilsk was built to run continuously decade after decade in Arctic darkness and cold. In one of the harshest climates on the planet, engineers didn't simply build a facility, they built an entire system capable of surviving where nature offers no margin for error. Number 6. Channel Tunnel. The Channel Tunnel, often called the Chunnel, is a 50.5-kilometer rail tunnel linking the United Kingdom and France beneath the English Channel. Completed in 1994, it remains one of the most ambitious underwater construction projects ever. And while the channel itself appears calm compared to polar or desert environments, the conditions beneath the seabed posed some extreme and persistent challenges. The tunnel passes through layers of chalk marl beneath the seabed, at depths reaching about 75 meters below the sea floor. Although chalk marl was chosen for its relative stability and low permeability, it still presented some major risks. High water pressure, variable geology, and the absolute necessity of preventing seawater ingress meant that even minor failures could have been catastrophic. Construction was carried out simultaneously from both the British and the French sides using these tunnel boring machines. These machines operated in confined underground conditions for years at a time, which advanced slowly while maintaining alignment. Any deviation could have resulted in missed connections or structural weakness, and constant surveying and recalibration were required. Seawater pressure increases with depth, so any breach down there could have flooded sections of the tunnel rapidly, so engineers relied on pressurized excavation techniques, reinforced linings, and continuous monitoring. The pumping systems had to be designed for worst-case scenarios, even though failure of those systems wasn't an option. Logistics were unusually complex. Excavated material had to be transported out continuously without interrupting the drilling. On the British side, millions of tons of chalk were processed and used to create new land at Shakespeare Cliff, turning the waste material into a coastal extension. That secondary project required its own engineering and careful planning. Once operational, the tunnel introduced some new challenges. Maintenance has to be performed without interrupting international rail traffic, and inspections are continuous. The environment down there remains aggressive, with saltwater pressure and vibration constantly acting on the structure. The channel tunnel is defined by sustained exposure to an unforgiving environment rather than any dramatic visual. Beneath the busy shipping lane and active sea, engineers created a stable, long-term transportation link where failure would have been immediate and severe. It's proof that harsh environments aren't limited to remote wilderness. Sometimes they exist just below the surface, where pressure, water, and confinement combine to make every engineering decision irreversible once construction starts. Number 5. Located in Cheyenne Mountain near Colorado Springs, the Cheyenne Mountain Complex was built during the Cold War. It was designed to function as a hardened military command center capable of surviving a nuclear attack. Construction began in the early 1960s at a time when tunneling technology was far less advanced than it is today. Engineers were tasked with excavating a huge network of caverns and tunnels more than 600 meters inside solid granite. The work required constant blasting and drilling, which generated intense heat and vibration. Ventilation was critical from the first day of the excavation, even as short interruptions could make conditions underground dangerous. The weight of hundreds of meters of rock above the complex exerted immense force on every surface, so rather than carving out rooms and lining them conventionally, engineers constructed a series of freestanding buildings inside the caverns. The structures sit on giant steel springs designed to absorb shock from seismic events or nearby explosions. The surrounding rock acts as a shield, but the buildings themselves remain mechanically isolated from it. Large-scale ventilation and cooling systems were required to maintain operating conditions for personnel and electronics, and the power systems had to be fully redundant, as failure underground could not be tolerated during an emergency. Water infiltration, too, was another issue. Even solid granite contains fractures, and groundwater seepage was unavoidable. Engineers installed extensive drainage systems to collect and redirect water before it could damage infrastructure. These systems are still active decades later as the mountain continues to exert slow pressure and moisture movement. Every piece of equipment down there, construction material and structural component, had to be transported through narrow access tunnels. Large blast doors weighing more than 20 tons each were installed at tunnel entrances to seal the facility from external shock waves. Workers had to spend long shifts underground with limited natural light, high noise levels, and constant vibration, so safety protocols evolved as the experience revealed new hazards, including rock falls, equipment failure, and air quality. Progress was steady but slow, and it shows the reality of working in an environment that resisted rapid excavation. Once operational, the complex became a central node for aerospace defense and early warning systems. Its design assumed that external conditions could become instantly catastrophic, which required the facility to operate independently. Food, water, power, and air filtration systems were all designed with long-duration isolation in mind. The result is infrastructure that functions precisely because it was built to accept those limits rather than fight them. Number 4. The Karakoram Highway is a high-altitude road that connects northern Pakistan with western China, and it stretches for about 1,300 kilometers through a mountain range. It's often referred to as the highest paved international road in the world. It passes through terrain shaped by some of the most powerful forces on Earth. The route follows river valleys carved deep into the rising mountains, particularly along the Indus River. These valleys are narrow, unstable, and prone to landslides, rockfalls, and flooding, and elevations exceed 4,700 meters at the Kunjerab Pass, where oxygen levels are low, temperatures can plunge well below freezing, and snow can block the road for months. Construction began in the late 1950s and continued for nearly 2 decades. At the time, the region had some minimal infrastructure and much of the work was carried out using basic equipment. Entire construction camps had to be built and supplied along the route, often reachable only by a narrow track. Machinery breakdown could halt progress for weeks, as replacement parts had to be transported over a huge distance. Geology here was the defining obstacle. The Karakoram lies at a collision zone between the Indian and Eurasian tectonic plates. Rock faces are fractured and unstable, and earthquakes frequently trigger massive landslides. Engineers couldn't eliminate those risks. Instead, they routed the road where terrain was least hostile, knowing that ongoing maintenance would be unavoidable. Bridges here had to withstand the extreme seasonal variation in water flow, including glacial melt and monsoon-driven floods. In some areas, entire sections of roadway have been destroyed and rebuilt multiple times due to slope failure or river erosion. The human cost of the build was significant. Thousands of workers labored in conditions where safety margins were thin and accidents were common. Despite the challenges, though, construction continued, driven by strategic and economic priorities shared by both Pakistan and China. Since opening, it's remained a vital corridor, but it's never truly finished. Landslide, avalanches, and flooding regularly close sections of the road, so modern upgrades, including widening sections, reflect the ongoing struggle. It's not a static piece of infrastructure. It's kind of like a living system that has to be rebuilt, reinforced, and adapted repeatedly. In a region where gravity, weather, and tectonics constantly reshape things, the highway is a reminder that engineering success sometimes means enduring rather than conquering the environment. Number 3. Vostok Station is located in the interior of East Antarctica, more than 1,300 kilometers from the nearest coast and over 3,400 meters above sea level. It sits on the Antarctic plateau above Lake Vostok, a huge subglacial lake buried beneath nearly 4 kilometers of ice. This station holds the record for the lowest natural temperature ever measured on Earth, -89.2 degrees Celsius, recorded in 1983. The environment here is not just cold, it's actively hostile to human physiology and machinery. The air is extremely dry, oxygen levels are low due to altitude, and winter darkness lasts for months. During the Antarctic winter, the station's completely isolated. No aircraft can land, no ground convoys can reach it, and evacuation is impossible under any circumstance. Construction began during the Soviet Antarctic expeditions of the 1950s and 60s. All building materials, food, fuel, and equipment had to be transported across the ice from coastal bases using tracked vehicles. Once delivered, construction crews worked in temperatures that limited exposure time outdoors to minutes. Structures were raised above the ice surface to reduce snow accumulation and drifting, and interiors were heavily insulated to retain heat. Even so, though, the temperatures fluctuated and frost formation inside the buildings is a constant problem. Power generation here is critical for survival. They rely primarily on diesel generators, which has to operate continuously to provide electricity and heat. Fuel storage and handling are major concerns as diesel thickens in extreme cold and mechanical systems are prone to failure, so redundancy is built into every critical system. Water supply too is another concern. Snow has to be melted for drinking water, which is a process that consumes energy and requires constant monitoring. Waste management too is strictly controlled to prevent environmental contamination, even in a place that appears lifeless. Every process here is shaped by the fact that resupply windows are short and unforgiving. Despite its crude appearance, though, compared to modern facilities, Vostok Station continues to function because it was designed around its environment rather than against it. There's no unnecessary systems here, no reliance on rapid repair, and no expectation of comfort beyond what's required for survival. It exists in a place where human presence is unnatural, and its continued operation depends on infrastructure that assumes isolation, failure risk, and extreme cold as permanent conditions rather than temporary obstacles. Number 2. The Baikonur Cosmodrome is located in southern Kazakhstan in a huge, sparsely populated steppe characterized by extreme temperature swings, powerful wind, and long distances from major centers. Built in the mid-1950s, Baikonur is the world's first and largest operational space launch facility, covering an area of more than 6,700 square kilometers. The climate here is unforgiving. Summer temps regularly exceed 40 degrees Celsius, while winter lows can fall between -30 and -40 degrees Celsius. Strong wind, dust storms, and sudden weather complicate both construction and launch operations. There was little natural shelter, and the flat terrain offered no protection from heat, cold, or wind. Construction began under intense political pressure, with limited time and incomplete infrastructure. There were no existing roads here, railways, or power systems capable of supporting a project like this. Everything had to be built from scratch: launch pads, fuel processing, tracking stations, housing, power plants, and water systems. Launch pads had to withstand the intense heat, vibration, and acoustic energy during liftoff, and fuel handling systems had to operate safely in both extreme heat and cold. So cryogenic systems, in particular, are sensitive to temperature variation and require precise control. Equipment breakdowns here could delay launches for weeks. Medical emergencies required a long transport time, and despite all that, the facility expanded rapidly, supporting the Soviet Union's early space program. Entire towns here were built to house the engineers, technicians, military personnel, and their families. Water scarcity required the development of long-distance supply systems. The aging infrastructure, environmental contamination from rocket fuels, and political agreements between Russia and Kazakhstan all affect how the site functions today. Maintenance in a harsh environment like this is ongoing and costly. It's not simply a launch site, it's a self-contained industrial ecosystem operating in a place where nature offers little support. In a landscape that's defined by heat, cold, and distance, Baikonur has launched thousands of rockets by relying on infrastructure designed to endure rather than avoid any extremes. Number 1. The Yamal LNG project is located on the Yamal Peninsula in northern Siberia, well above the Arctic Circle. This region is defined by continuous permafrost, polar night, and winter temperatures below -50 Celsius. Building one of the world's largest liquefied natural gas facilities under those conditions places this among the most extreme industrial projects ever completed. Construction began in the early 2010s on terrain that can't support traditional foundations. Permafrost becomes unstable when warmed, and even when small heat leaks can cause ground subsidence. Engineers had to address this by using thousands of deep piles driven into permanently frozen layers. The entire facility is effectively built on stilts to preserve its ground stability. Most large components were fabricated elsewhere and then transported by sea using ice-class vessels during short summer windows, so modular construction was essential. Entire processing units, some weighing thousands of tons, were assembled off-site and delivered to Yamal for installation in a compressed time frame. Machinery had to function in the extreme cold, where steel becomes brittle and hydraulic systems fail easily. Construction schedules were planned around the temperature, when certain tasks were impossible below specific limits. Workers had to operate under strict safety protocols to prevent any cold-related injuries, and heated shelters were mandatory near active work zones. Worker camps, power plants, and port facilities were constructed alongside the processing trains. The port of Sabeta, built specifically for Yamal LNG, required dredging and ice management systems to remain operational in these frozen seas. But once operational, Yamal LNG relies on a fleet of specialized ice-breaking LNG carriers capable of navigating the Arctic waters year-round. Those ships represent an extension of the megaproject beyond land, integrating marine engineering into the system's design. Yamal LNG is ranked number 1 because it combines every defining element of harsh environment construction: extreme cold, unstable ground, isolation, and the scale of it. It's not a temporary installation, it's a permanent heavy industry operating where failure has consequences. In one of the least forgiving regions on Earth, Yamal LNG shows how modern projects succeed only by designing every component around environmental limits that can't be negotiated or ignored.